In this tutorial, I'm going to be going through an introduction to work and energy, along with some practice problems. So, energy gives us a different perspective on physical situations. In the past, when we talked about forces and acceleration, we would usually freeze the object in motion. So, with forces and acceleration, we would have some kind of object. So let's say there's this mass. We'd label it with a free body diagram. Let's say there might be a push. So the force of the applied push. Maybe there's friction on the surface. So we have kinetic friction. We have the weight of the object. And we have a normal force acting on the object going upwards. So the approach to forces and acceleration would usually involve drawing a free body diagram, creating a coordinate system, for example, x and y being positive, and then using Newton's second law to create your F equals ma equations for each direction x and y. But with work and energy, all we really care about are the initial and final conditions. So the approach to work and energy would be looking at what happens at the beginning and what happens at the end. So you usually have an initial scenario. Maybe you have your block over here on the table, and it's at a certain height. So we have height initial, and it has a certain velocity. So we have an initial velocity of an unknown amount. Then you have your final scenario. So maybe your block is now all the way over to the right of the table, moving at a final speed that's greater than the initial speed, and ending up at a final height. So with approaches to work and energy, we have to look at things a little bit differently. We look at the initial and final conditions separately, and we don't worry about what happens in between. Moving on to work, we should start with a discussion of what it is and what the equations are. So with work, whenever you apply a force to an object and cause the object to move, work is done by that force. So we can define work as the following. So work is defined as W equals to FD cos theta, and theta is the angle between force and displacement. Just keep in mind that force and displacement are both vectors. And all vectors are going to have magnitude and direction. In the work equation, if you use W equals FD cos theta, F and D are both going to be the magnitudes of the vectors, but in order to get theta, you do have to realize and determine which directions force and displacement go in. So, for example, you might have a force being applied to your object in this direction, and maybe your object is moving towards the right, in which case it is being displaced towards the right. So the displacement vector would be towards the right as well. So then the angle we're talking about would be theta over here, the angle between the two vectors. So by looking at this equation, W equals FD cos theta, Number one, we can figure out the units of work. So force is given as newtons, and displacement is given as meters. So you have Newton meters for work, which is given the common name of joule. The other important thing to understand is that the cosine function can give you positive or negative values. So we have cosine of theta can give us positive or negative values. And because of that, it means that work can be positive or negative. So as a result, it's very important to recognize which force you're analyzing work for and what direction that force is facing with respect to the motion of the object. So let's start off with a practice problem. So this one is about a boy that exerts a force of 11 newtons at 29 degrees above the horizontal on a 6.4 kilogram sled. It starts from an initial speed of 0.5 meters per second, and the sled moves a distance of 2 meters. We're supposed to find A, the work done by the boy, and B, the final speed of the sled. So for any work and energy problem, the same first step is usually required, which is to draw a diagram. So we have step number 1. Draw a diagram. So we know we're looking at a sled, and we know the boy is pulling a sled, which means that if you're pulling something, most likely the object is behind you and you're pulling with an upwards force. So why don't we first start off by drawing the ground, and the object on the ground, which is the sled, which we'll call M for mass. We know that the mass of the sled is 6.4 kilograms. And we know that there's a force that's being applied to the sled. So it's going to be a pulling force at 29 degrees above the horizontal. So let's just say we have the force of the pull being 29 degrees, or to keep it generalized, we have theta over here, and theta is equal to 29 degrees above the horizontal, with the magnitude of the pull being 11 newtons. So make sure that's a vector. We're also given a few more pieces of information. It starts from an initial speed of 0.5 meters per second. So we know that V initial is equal to 0.5 meters per second, and the sled moves a distance, or delta x, of 2 meters. The one thing we've really forgotten to label here is the displacement vector, because for work, if we're trying to find work in part A, we do need to know which direction the object is moving. So when we labeled the force of the pulling, so this one over here, we also know that the object might be moving in this direction, so this would be our displacement vector. This now gives us enough information to try and attempt part A. So let's go to step 2. Find the work done by the boy. Also keep in mind that whenever you're trying to find the work done by something, it's always going to be associated with some sort of force. The boy is applying a pulling force, which is F pull. So we want to find the work done by that force in particular. So we have the work done by the pulling force is equal to the magnitude of the pulling force times the magnitude of your displacement times cosine of theta. So it seems like we do have the magnitude of the pulling force, the magnitude of displacement, and also theta. So we can just go ahead and solve. The pulling force is 11, the displacement is 2, and we have cosine of 29 degrees. If you punch that into your calculator, you get 19.2 joules. And that would be your answer. This means we can move on to part B, which is asking for the final speed of the sled. So let's go to step number 3. Find the final speed of the sled. To find the final speed of the sled, there is one equation that we have learned before, and that is W total, or W net, is equal to delta KE. So this equation is derived from the conservation of energy equations, but for this, it basically means there's no potential energy we have to care about because the mass is on the same level ground, so there is no change in potential energy, and the only force being applied to this system that's external is the force of the pull. So now we have the work done by the pull being equal to the change in kinetic energy. So that is 1/2 mvf squared minus 1/2 mvi squared. And this is something we'll talk about after in more detail. We're trying to find the final velocity over here, so we rearrange the equation to get 1/2 mvf squared is equal to W pull plus 1/2 mvi squared. Then we have Vf is equal to the square root of 2 W pull plus 1/2 mvi squared divided by m. You then plug in the values that we have, which is 2 times 19.2 plus 1/2, 6.4. The initial speed is 0.5. And mass is 6.4. Your final answer for your final velocity is going to be 2.5 meters per second. Now I want to move on to conservation of energy. This is probably the most important part of work in energy because as long as you understand this part, most types of questions will fall under this category. So first of all, in class, we've learned about several types of energies, primarily kinetic and potential energies. So kinetic energy is the energy of movement, while potential energy is the stored energy of position. So I want to write down what types of energies we've gone through. We have kinetic energy being the energy of movement. We also know that kinetic energy is given as Ke equals 1/2 mv squared. We also have potential energy. So this is the stored energy of position, and typically we use PE to represent this. However, there are two types of potential energy we have to be aware of. So there's gravitational potential energy and spring potential energy. You'll have to determine whether only one, both, or none of these types are involved in a situation when you read the question you're trying to answer. So this is split up into two. We have gravitational PE and we have spring PE. So this one is called PE. The potential energy of gravity is equal to mgh. The spring potential energy is given PES, and that's equal to 1/2 kx squared. So the key thing to remember here is when you're talking about gravitational potential energy, you care about the height. Of an object. If there is a change in the height of an object, then there is going to be a change in the gravitational potential energy, and that means you should care about this when you do a question. When we look at spring potential energy, we have K and X being, so we have X being the displacement of the spring. So either it's stretched or compressed from equilibrium. And by that, I mean we have a spring, and let's say this is its equilibrium position. So if it goes this way or that way, it could be positive or negative depending on your coordinate system. K is the spring constant. That comes from Hooke's law. F is equal to negative kx. This means that K has units of newtons over meters. So these are important values to know, and essentially if there is a spring in your question, you should include the potential energy of a spring as well. So the last thing is something called mechanical energy. So we have mechanical energy being the total of kinetic and potential energies of a system. So this means delta ME is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. Moving on, we now want to talk about the conservation of energy. In a perfect world, the law of conservation of energy applies, and the total mechanical energy of a system doesn't change from beginning to end because everything is conserved. So let me just write down, in a perfect world, we have delta ME being equal to 0 because all the energies are conserved, which means that you can solve your question by setting up delta ME is equal to delta KE plus, for simplicity, I'll just combine PEG and PES into delta PE for a change in potential energy. If we know that it's a perfect world scenario with no friction and no external forces being applied to the system and everything is conserved, then we know that the change in mechanical energy is equal to 0. And therefore, you can then solve for any variable in here or here and rearrange to get your answer. Now we move on to what happens in the real world. So in the real world, the change in mechanical energy is not going to be equal to 0 because you can either add or take away energy from a system in most cases. This means there must be a external work being done or, I guess it should be and, or B, work done by friction on the system. So this would take away some energy from your total amount. The last portion I want to go through are two different approaches to solving questions. There are essentially two main approaches to solving energy and work-related questions, and it's better to pick the one that makes the most sense to you. Method number 1 involves analyzing mechanical energy. In this method, we use delta ME is equal to delta KE plus delta PES, or G, plus delta PES. So just keep in mind, if you only have either gravity or springs acting on a system, you can simplify this by writing delta PE if there's only one type acting on the system. So step 1 for these types of questions, you first want to find the initial versus final values of delta of KE, PEG, and PES. In step 2, you want to determine if there is any change in mechanical energy. So that means if everything is conserved and there is no friction and no external work being applied to the system, then your change in mechanical energy should be equal to 0. And if not, you have a change in mechanical energy not being equal to 0. So this would be, once again, the perfect world scenario, and this would be the real world scenario. From here, if delta ME is equal to 0, you can usually rearrange and solve for your answer immediately. Because it would just be delta KE equals to negative delta PE. If delta ME is not equal to 0, we have to move on to step 3. In step 3, we have to equate delta ME to the work done by some other force, such as WK for the work done by kinetic friction, or WEXT, which is the work done by an external force. So this summarizes one method of solving work energy equations. And this method means that you have to come up with the equation yourself in order to solve. There is another method, which we'll call method number 2, which requires you to adapt a general energy equation. So in this method, we're using WEXT minus the absolute value of WK is equal to the change in kinetic energy plus the change in potential energies. So it could be PEG plus delta PES. So as you can see, it's very similar to method number 1. It's just that it has everything split up for you already. The left side is simply just the change in mechanical energy, just broken up into the work done by an external force and the work done by kinetic friction. If you prefer having an equation to use from the get-go, this is the one I would recommend. So here, with step 1, it's the exact same thing. We're finding the initial versus final values of KE, PEG, and PES. There's no difference whatsoever. In step 2, instead of determining whether the change in mechanical energy is 0 or not 0, we look at it a little bit differently. We're going to just see if there is any external or frictional work done on the system. And if so, keep the WEXT or WK terms. If we're comparing these two methods, step 2 is very similar to step 2 in method 1 and 2. In the one that we're looking at right now, if we're in a perfect world situation, there is no external force and there's also no friction, which means that the left side of the equation becomes 0, and in other words, delta ME is equal to 0. If there is external work or friction being done on the system, then that means there is going to be a value on the left side of the equation, which means that delta ME is not equal to 0. So the last step for this new method, method number 2, is to update the energy equation to suit your needs and whatever the question requires, then solve. This question helps us practice using the conservation of energy equations. So a 55 kilogram skateboarder enters a ramp moving horizontally with a speed of 6.5 meters per second and leaves the ramp moving vertically with a speed of 4.1 meters per second. Find the height of the ramp, assuming no energy loss due to frictional forces. The first thing I see here is that there's no energy loss due to frictional forces. That really tells me that WK, change that to another one, color, WK is equal to 0. We're also looking at just a skateboarder that enters a ramp and leaves the ramp. There's no other forces acting on the system, so we can say there are also no external forces acting on the system, so no work being done by an external force. This all tells me that this is a perfect world situation, so the change in mechanical energy is going to be equal to 0. So the first step, I want to draw a diagram. So the skateboarder enters a ramp going this way with an initial speed of 6.5 meters per second. The skateboarder then leaves the ramp moving vertically with a speed of 4.1 meters per second. So this ramp is going to have some sort of shape that looks like this. And the ramp also needs to have some sort of height. So we have the height of the ramp being like this, with the initial height being 0 and the final height being an unknown quantity that we have to find, but we can call this h. So now, the first thing we do, according to our method, is to analyze the initial and final conditions of this scenario. So the initial condition I'll label as I, and the final condition I'll label as F. And then we'll do an analysis elsewhere. So step 2, we have initial versus final conditions. I for initial, and F for final. So with our initial conditions, we know that VI is equal to 6.5 meters per second, and we know that HI is equal to 0 meters. In our final condition, we know the skateboarder has a final speed of 4.1 meters per second and a final height of h. So there are essentially no springs involved in the system at all, so we can forget about PES entirely. So that means we only care about kinetic energy and gravitational potential energy. So KEI, which is the initial kinetic energy, is equal to 1/2 mvi squared, and the potential energy, which is just gravitational potential energy, is going to be mgh. But h is equal to 0, so we have 0 for this. Now we look at the final scenario or final conditions. We have KEF is equal to 1/2 mvf squared, and we have PEF being equal to mgh. So now we have our initial versus final conditions. Step number 3 is going to involve using an energy equation of some sort. In this case, if you're using method number 1, you're going to use delta ME equals 0. If you're using method number 2, you're going to use the WEXT minus WK method, which gives you the same answer. So here we know that we have delta ME is equal to delta KE plus delta PE. We know that this is 0, and we know that we have a change in kinetic energy, which is 1/2 mvf squared, for KEF minus KEI, which is 1/2 mvi squared, plus PEF minus PEI, which is mgh minus 0. So what are we trying to find? We're trying to find the height of the ramp. So we're actually trying to find what h is. So we should probably rearrange and solve for h. So we have mgh is equal to 1/2 mvi squared minus 1/2 mvf squared. And we have h is equal to 1/2 m vi squared minus vf squared divided by mg. We can then plug in our values. We have 1/2. The mass of the skateboarder is 55 kilograms. And we have the initial speed being 6.5 squared minus 4.1 squared divided by 55 is 9.8. And so the height, once you punch that into the calculator, you get 1.3 meters as the height of your ramp. Moving on to another question. This one's a little bit more complicated with a pulley system. So in this case, we have a block of mass M1 on top of the table, which is 22.4 kilograms. You then have a second block that's hanging, which is 11.8 kilograms, to the right of the table. When the blocks are released from rest, which means they both start off with a speed of 0 meters per second, they move through a distance of d equals 0.5 meters, at which point the second block hits the floor. Here we do have the coefficient of kinetic friction being 0.45 between the first block and the surface, and we're supposed to find the speed of the blocks just before M2 lands. So considering this is the work and energy topic, we should probably use a work and energy approach for this. So step number 1 usually is to draw a diagram, but the diagram is already provided to us, so we should probably label it and also try and figure out the initial and final conditions. So step number 1, initial versus final conditions. Now this diagram has already labeled the initial and final stages. So we'll just highlight I in red and the final condition in blue. So we have initial and we have final. The main difference between the previous problem and this problem is that we now have two masses to look at, which means when we're looking at the initial kinetic energy, we're looking at the kinetic energy of both blocks separately, and then adding them to get the total initial kinetic energy, for example. So let's look at mass 1. Mass 1 is going to have an initial kinetic energy. So let's say KE1I for the initial kinetic energy of the first block is equal to 1/2 mv1I squared. So that's the initial velocity of the first block. So before we even move on, we should probably go back to the diagram and start labeling everything that we're given. So for mass 1, we know that for the initial condition, V1I is equal to 0 meters per second. We also know for the initial condition for the second block, we have V2I is equal to 0 meters per second. We should probably look at height now. There's no springs involved, so we don't care about those. The height of the first block initially is going to be h. The height of the second block initially is going to be d. So now we can look back at our table and label everything we want and put it into the equation. So here, V1I is equal to 0, which means KE1I is 0. We should look at the potential energy of the first block initially, which is mgh1I. That is equal to h, so we have mgh. We then look at mass 2. We have KE2I is equal to 1/2 m V2I squared, but V2I is equal to 0, so we have 0 here as well. Writing this out, you might notice one thing. I've forgotten to label the masses with mass 1 and mass 2. This is extremely important. So now I really should look at mass 1 and make sure I make the difference between my equations. And mass 2 has m2 in it for the mass. Now we have PE 2I is equal to m2g h2I, and we know that the height of the second block initially is going to be d, so we have m2g times d. So now when we look at this, the total kinetic energy initially is KEI is equal to 0 plus 0 for both masses, which is equal to 0. And we have PEI for the total initial potential energy is equal to m1GH plus m2GD. So these two are the most important equations moving forward when we create our finalized energy equation. So looking at our final conditions, in the diagram, the final speed of the first block, v1f, is equal to an unknown value. The final height of the first block is still going to be h. It's on a table. It didn't go anywhere else. Here, for the second block, we have v2f being the final speed of the second block, which we're trying to find. We don't know that yet. And we have h2f being equal to 0 because it hits the ground. Before we move on back to the table in step 1 again, there's something else we want to analyze, and it's whether these final speeds for both the blocks are the same or different. Because both of these blocks are attached by a string, we can assume that they're going to have the same speed at the beginning and end. So here we should make the assumption that the final speed is just Vf for both mass 1 and mass 2. Now we can go through everything again for the final conditions. For mass 1, we have Ke 1f is equal to 1/2 m1 v1f squared. But we know v1f is equal to vf, so let's just say 1/2 m1 vf squared. Pe1f is equal to m1g h1f. We know this is still h, so we have m1gh as our final value. We then look at mass 2. We have Ke 2f is 1/2 m2 v2f squared. But we know that the final speed is just vf. So we have 1/2 m2 vf squared. The gravitational potential energy is going to be m2g h2f. We know that h2f is equal to 0, so this is just 0. So that means the total final kinetic energy is going to be 1/2 m1 vf squared plus 1/2 m2 vf squared. And the total potential energy in the final condition is m1gh plus 0, which is equal to m1gh. Moving forward, these are the most important ones we want to look at now. So step number 2, we'll go over here. Involves setting up the energy equation. So the energy equation is delta ME is equal to delta KE plus delta PE. We already know we can solve for the right-hand side because we have KEI, KEF, PEI, and PEF. So we can create an equation based off of that. However, one of the things we don't know yet is what is delta ME. So we have to take a look at what additional forces are at play in this system. And the only additional force at play is going to be WK. So that means the only thing acting here or the only contribution is from frictional force. So delta ME is equal to WK, which is equal to the work done by a frictional force. So there's no WEXT, or WEXT is equal to 0, but there is WK, which means we have WK is equal to KEF minus KEI plus PEF minus PEI. The only thing is we're given the coefficient of kinetic friction, so we should probably figure out what this is so that we can find out what the speed of the blocks are, or else we'll be stuck in this question. So another way of representing the force of friction, or the work done by friction, is as follows. So work done by friction. If we have our block M1, we know it's on a surface, so we have M1G as the weight. We'll have a normal force pushing back up on us. We're going to have friction here. And this is all we care about. If I want to find the work done by kinetic friction, I only care about FD cos theta. So we have the frictional force being defined as mu k n. We have some sort of displacement, and we have cosine of theta. But here, there's no vertical acceleration in the system, because if we take a look at the y direction, the n and the m1g will have to cancel out, so n is equal to m1g, based on what we've learnt through forces and Newton's law. So we now have mu k times m1g times d cosine of theta. So d, what is d? It's probably the distance traveled by the block, which is going to be the same as the height traveled by the second block. So we already have d, which means we don't have to worry about it. That means here we can plug this in so that we have mu k m1g d cosine of theta. is equal to KEF, which was 1/2 m1 VF squared plus 1/2 m2 VF squared, plus PEF, which is m1 GH, minus PEI, which is minus m1 GH minus m2 GD. Okay, just make sure you double check for your signs. So looking at this, there are a few things I can cancel out. m1GH minus m1GH, they can both go. The rest, not so much. Cosine of theta is something we can get from our free body diagram that we just drew. We know that this is going to be the displacement vector because mass 1 is going to move towards the right, which means if we analyze Fk and D, we have an angle of 180 degrees. And the cosine of 180 degrees is equal to -1. So we can replace this with minus mu k m1GD is equal to 1/2 m1 VF squared minus 1/2 m2 VF squared minus m2 GD. So the goal is now to solve for VF. We can probably combine both the VFs together. So let's move m2GD over. So we get mu k m1GD. And that is equal to VF squared 1/2. We could probably have 1/2 VF squared m1 minus m2. So just looking back, I think I didn't make a mistake at the beginning because KEF is 1/2 m1 VF squared plus, so that was my bad. Make sure these are pluses. We can then solve for VF squared is equal to 2 m2GD minus mu k m1GD divided by m1 plus m2. VF is going to be the square root of 2, I can take out the GD as well, m2 minus mu k m1 divided by m1 plus m2. Then I have 2 times 9.8 times D, which is a distance of 0.5 meters. M2 is 1.8 minus 0.45 times 2.4 divided by 1.8 plus 2.4 for our two masses. Once you plug that into the calculator, you should be able to get 1.3 meters per second for your final velocity. With all the questions we've done so far, we haven't really touched on springs at all, so we should probably do a question with springs. So in this question, we have a 1.8 kilogram block that slides on a rough horizontal surface. So we know that there's friction here, and we know that there is going to be a spring because the block hits a spring with a speed of 2 meters per second and compresses it a distance of 11 centimeters before coming to rest. So the keywords here, we have it comes to rest, which means the final speed should be 0. There's a rough horizontal surface, which means there is friction involved, which means we are going to have some sort of work done by kinetic friction. It says that the coefficient of kinetic friction between the block and the surface is 0.56, and we're trying to find the force constant of the spring, which is K. So, the first thing we should do is draw a diagram because it's not provided to us. We know we have some sort of ground, which has an initial height of 0 to make things easier. It also says the block is going to hit a spring so we have a horizontal spring something like this. And let's say that there's going to be a block of mass m that compresses it. So in terms of the compression, it says that it has compressed at a distance of 11 centimeters before coming to rest. What I've drawn here is probably the final condition, because it looks like it has already compressed the spring by a certain amount. So let's say that the compression is going to be from here to here, where this is equilibrium, so x equals 0, and therefore it has been compressed by an amount x, where this is x equals to x. This also means that there is going to be a block here in the initial stage. So this is initial, and this is final. So in the initial stage, we have Vi is equal to 2 meters per second. In the final stage, we have Vf is equal to 0 meters per second. We know that the height of both initial and final conditions doesn't change at h equals 0, so we can assume that there is no gravitational potential energy involved. So here we can immediately say delta PEG is going to be 0. So the only thing we care about is going to be delta PES and delta KE, because the kinetic energy has changed. We know that M is equal to 1.8 kilograms, mu K is equal to 0.56, and we know that X is equal to 11 centimeters, or in SI units, we have to convert to meters, so it's 0.11 meters. So now, in step 2, we can probably analyze the initial versus final conditions. So initial versus final. In the initial condition, we do have KE I is equal to 1/2 mVi squared. So this is a non-zero value, We then have PEI, which is equal to 1/2 kx squared. But we know that x is 0 at the beginning, so we have 0 over here. Oops. Next we have final. So that means we have KEF equals to 1/2 mvf squared. The final speed is 0, so we have 0 here. We have PEF being 1/2 kxf squared. We know that the final distance traveled by the spring, or the total compression of the spring from equilibrium, is x, so we have 1/2 kx squared. Now in step number 3, we can come up with our energy equation. So that means delta ME is equal to delta KE plus delta PE. The thing is, delta ME in this case, what are the contributions that cause a change in mechanical energy? The only contribution we can see here is from the frictional force. So that means WK is equal to delta ME, and that means we are going to have to find what WK is equal to. So in order to have WK being equal to KEF minus KEI plus PEF minus PEI, we're going to have to figure out an expression for WK. So the work done by friction, we have our mass, we have mg, and we have a normal force because it's on a surface. We know that the frictional force is going to be in this direction, and we know that the displacement is going to be in this direction. So we know that theta is equal to 180 degrees, just like before, and that means we can come up with an equation for the work done by kinetic friction, which is Fk d cos theta. We know that Fk is going to be equal to mu kn. The displacement, or the distance traveled or compressed, is going to be x, and cosine of 180 degrees is -1. So we then have minus from the cosine 180 of -1 minus mu k. We know that there's no vertical acceleration, so we have n being equal to mg, and then x being x. So now we can replace this with negative mu k mgx is equal to KEF, which is 0, minus 1/2 mvi squared plus 1/2 kx squared minus 0. So our goal is to try and find out what k is. So we're going to rearrange and solve for k. So let's do 1/2 mv1 squared minus mu k mgx is equal to 1/2 kx squared. Then k is going to be equal to 2 times 1/2 mvi squared minus mu k m gx divided by x squared. When you plug in the values, you get 1/2. The mass is 1.8 times the initial speed of 2 squared minus 0.56, 1.8, 9.8, and the distance of compression of 0.11 divided by 0.11 squared. Punch this into a calculator, you should get 415 newtons per meter.